on this equation here for the system, and you've got an equation or an equation right here you want to keep an eye on, delta H is negative. So as I'm reading a problem, I always underline, circle the things that are important, okay? For the production of SO3. Assume that one has an equilibrium mixture of these substances. Predict the effect of each of the following changes on the value of the equilibrium constant. So what are we going to be using? We're going to be using Le Chatelier. Okay, we're going to be using Le Chatelier. Okay, predict the effect if on the number of moles of SO3 present in the mixture at equilibrium. So we're talking about SO3, what's going to happen to it. Briefly account for each of your predictions. Assume in each case all other factors remain constant. So the first one is I'm going to decrease the volume of the system. So I'm going to rewrite this because I want to see it with a little bit bigger for me. And I want to put delta H in there so I know where it's at. So if delta H is negative, then I'm going to have heat on this side, right? If it's negative, it goes on the product side because it's giving off, it's exothermic. If it's positive, I put it on the reactant side because I have to put it in. Okay, so A is all about the volume of the system. If I'm decreasing the volume, then that has to do with the number of moles. So the number of moles of gas on the reactant side are how many? Three. So 2 plus 1 is 3. How about on the product side? 2. So I can show that really quick that I know that the number of moles of gas is going to be different. And I can say SO3 gas will increase. Why? Because they always want you to answer, explain, right? Because you're not going to get the point unless you tell them why. So SO3 will increase, but that's not, I have to explain it. As volume goes down, pressure goes up, favoring lower number of gas molecules. Right? KQ does not change. So let's look at.
So why does a higher pressure favor lower? Oh, because it's pushing it out, right?
You've got 3 versus 2 people. If I'm shoving them in a closet, 2 is a lot easier to get in than 3. Okay? So it'll make it be 2. All right, so adding oxygen. So this is where I'm using my arrows. If I add oxygen on this side, I put a pressure on that side of the reaction. Which way is it going to shift to relieve the pressure? I'm adding oxygen on this side. So I'm putting a pressure on this side of the system. What side is it going to shift to relieve the pressure? It's going to shift to the other side. So in B, what are we going to say about that? They want to know what's going to happen to SO3. So what's going to happen to SO3? Increase, right? It'll increase. Why? So it's going to relieve the stress on the system, and KQ again remains constant or stays the same. The only thing that will change KQ is temperature. So that sort of leads into the next one. So if I'm adding heat to the system, I'm adding heat in here, I'm putting a stress on the system, which way is the system going to shift? The system's going to shift that way to relieve the stress, right? So what's going to happen to SO3? This one's going to decrease. Okay, I've got to give a Y. Because I'm putting heat in here where you want to give it away, and they're putting heat in. So because I'm putting heat in where I want to give it away, it's going to shift them back to the reactants. Okay, so I'm going to decrease to relieve the stress again, but this time, what happens to KEQ? KEQ is affected here. It becomes less because I have less product. Remember, we're products over reactants. Now, the others do shift, but they shift to go back to equilibrium. Okay? Okay. All right, let's look at the next one. All right, so we'll start this again. What are we seeing right now? Okay, so sulfur chloride is highly reactive gaseous compound. When heated, it decomposes according to the following equation. This decomposition is endothermic, meaning it needs heat. So delta H is positive, so I can put up here delta H positive. A sample of, there's something I might need later, is placed in an evacuated ball. Here's something I might need later. And the temperature is raised to this. So you just said what? Pervert, right. So A is going to be PV equals nRT. What are we solving for? Pressure, yep. So pressure is going to equal nRT divided by V. I'm going to stop it for a minute. I want to see if you can make it all the way through to the end. Okay, so I gave you time to figure it out on your own. Okay, what did you get? Oh, okay, just a sec. He wants one more second. So I'm going to put this up real quick. So you should have okay, so if you set it up just like this, you should be ta-da! How'd we do? Of course, we wouldn't circle it, right? Because we know better. I'm looking for ATM. Oh, I took it too many. 0.80. There we go. All right, so second one. The second part of this question says, when a system has come to equilibrium at, so there's that temperature again, the total pressure in the bulb is found to be this. Calculate the partial pressures of this, and this at equilibrium. Okay, so what do we just solve for? We just solved for the pressure of this if there was no dissociation. So guess what?
Don't we have to?
It's sort of like ice, only, yeah, well, basically it is ice. So so we have SO2Cl2 going to SO2 plus Cl2. And if we set up a quick ice, initially, what we just solved for, we had 0.800 with nothing here and nothing here. Then the C, because it said assuming no dissociation. So then the C is the change. So some of it's going to have to shift from over here, and it's going to end up here and here, right? And since they all have ones, it's just minus x and plus x plus x. Because this had some, this didn't have any. So this has got to shift, the left has got to shift to the right. I just don't know how much. And for every 1 mole of this, I'm going to get 1 mole of this and 1 mole of this. So then for my equilibrium, I'm going to have 0.8 minus x plus x and plus x. Whoops, that's a bad plus x. Are we okay? Okay, but I'm not doing equilibrium. What did it ask me? Good. So it's set up here. I got 1.43. That's my pressure total. Well, if I remember Dalton's del law, all the pressure total is equal to all the little parts added up, right? So 1.43 is going to be equal to 0.8 minus x plus x plus x. Right? Now solve for x. It's pretty easy because that x and that x will cancel each other out. Negative and positive. So then I'm coming down here and I have 1.43 equals 0.8 plus x. So x equals what? And so I can say right now that this is the pressure of SO2, which is also equal to the pressure of Cl2. And then to solve for the pressure of SO2 and Cl2, I just take and subtract 0.8 minus 0.63, and I get 0.17, right? And these are all ATM. So I just did this. I plugged x in here, right here. I plugged x into here to get that.
Oh, because the pressure of the actual substance is kind of like that higher.
Right. So let's go back up, see what it was asking, make sure we answered it. So it wanted the partial pressures of each of those. So I just did that, right? And I gave the unit, which was atmospheres. So next one, give the expression for the equilibrium constant, Kp or Kc, for the decomposition of this. Calculate the value for the equilibrium constant you have given and specify the units. Since I've already got the pressures, I would do Kp, just because it's easier right now. So we're going to C. I would set up Kp because they usually give you a point for just setting it up. So it would be products, which are SO2. Whoops, let me not do it that way. That's Kc. Pressure of SO2 times the pressure of Cl2 divided by the pressure of SO2Cl2. And then just plug and chug. See if you can get the answer. Mm-hmm. So I'm going to stop, plug and chug, see if you can get the answer. Okay, so if you plugged it in like this, what did you get? 2.3. Actually, KP, it will have atmosphere, sorry. They did have atmospheres on it. Because this will be atmospheres squared, and this is atmospheres, so one of them will cancel. So that one did have a pressure unit. Okay, and the last question that I didn't copy to be at the top, it said if the temperature were raised to 500 degrees Kelvin, would this have an effect on the equilibrium constant? Let's look up at the top. What did we learn up at the top? Delta H was positive. So how's it going to affect my equilibrium constant? You said yes, so D, yes is right. Yes, because what? So K at 500, how's it going to compare at the K that we just did that was at 375? Be larger, okay? And we say that because, again, to reduce the stress on the equation that the heat caused. And it was an endothermic reaction. So it would force it forward. Okay. Let's do another one, 1985. Go to another page. We okay? This is good? Okay, here's 1985. Take a second, look at it, and see what we can bring out of it. Okay, solubility. Okay, so we know that we're going to go for KSP. Now remember, all of them, all the Ks are set up the same, products over reactants. We drop out liquids, we drop out solids. So for strontium sulfate is this. So that's probably something I need to know later. Okay, the solubility product constant for strontium fluoride is this. What is the molar solubility of strontium sulfate in pure water at 25 degrees? So I'm looking at strontium. I want to do the equation for strontium sulfate. So for A, strontium sulfate as a solid is going to dissociate into what? What ions? What column is strontium in? It's in the second column, so it's going to be a +2, right? And that's going to be aqueous because it's a cute little ion. So that leaves what? Sulfate, which hangs together, SO4 as a -2, has a cute little ion. So if I were to write the KEQ for this, KEQ is going, actually it's going to be KSP, right? KSP because it's K of solubility. It's going to be equal to the concentration of SR +2 times the concentration of SO4 -2. It's a 1-to-1 relationship, right? So I can say that SR plus 2 is equal to the concentration of SO4 minus 2, which I'm going to call X. Okay. Okay, so all I did was I split the solid up into its ions. Okay. Once it's in its ions, now I'm going to do a K for it, products over reactants. So here's my products. The reactants are solid, they drop out. Okay. Now,
The solids drop out?
yes, solids and liquids drop out.
Solids and liquids. So gases.
Gases stay and aqueous stay. Okay, so because the molar ratio is a 1-to-1, and for every one of these that breaks up, I get one of these and one of these, right?
Yeah.
Okay, so because of that, I can say these two are equal. Because they're equal, I'm going to just call them X. I don't know what they are, but I'm going to call them X. So because I do that, I can say KSP is equal to X squared, right? Well, I know what the KSP is. It's up here at the top, right here. So I can say that's equal to 7.6 times 10 to the minus 2. And I can solve for X. How do I solve for X? I square root each side. And I get X is equal to what? Square root each side, because I want to get X by itself. I want to just be X. I want to be the answer for X. Yep. So what do we get for the answer? So if we were to put that in scientific notation, hopefully it will be this. Is that what you got? And it is concentration, so it's molarity, and that's the solubility of SR-SO4. Having problems putting it in? So you're going to use your blue button. Somebody didn't get out of the easy data to go, if you got a TI, to go second function, you're going to do that first to get your square root, and then underneath the square root, put in parentheses 8.7, I'll try it again, 7.6 times 10 to the minus 2, and then close parentheses. And I didn't get what they got. I got 0.275. They must have messed up because that, oh, because this is a -7 right here. We didn't read that right. This is a -7. So put that as a -7.
That's not fair. What if they do that on an AP test? Like, I thought that was right.
Well, hopefully,
Answer, right?
if now I get that answer, yes. Okay, I was like, this is really screwed up. Okay, so now let's go to the next part of it. So what is a molar solubility for SRF2? I'm going to pause it because you know how to do it now. Now, here's the caution. You get 2 F's, right? So when you get 2 F's, you got to put a 2. If you get a 2 here, you got to put a 2 here in front of the X. Okay? So I'm going to let you try and do B, and then we'll come back and do it together. Okay, let's see what we did. So on this next one, whoops, I'm on the wrong pen here. Try this kind of pen, B. So we have strontium fluoride, right? Is it strontium fluoride? Strontium fluoride, and it's a 2 solid. It's going to break up into strontium plus 2 AQ plus 2 F minus AQ. Now they usually give you 1 point just for writing that out right. Okay? Then to do the KSP for this one is a little bit different. KSP for this one is the strontium, just like it was up above. Okay? But we have 2 fluorines, and it's going to be squared. There's a subscript. But the other one, the group stuck together. SO4 stuck together.
Oh, so if it's like...
So if it's a polyatomic and it sticks together, it just sticks together. If it's an element, then it splits apart. So here I've got to say strontium, I'm going to say is equal to X. So I'm going to get one of them. But fluorine, I've actually got 2 of them. Right? So for every strontium, when I break this up, I get 1 strontium and 2 fluorines. Does that make sense? No, it's just 2X right here. Now I'm going to plug that back in for the fluorine and the strontium. So as I do that, I really wouldn't have written, I did this to write it to start with, but I really wouldn't have written that 2 there, right? I did that to try and help us. Okay, so we're going to get X times 2 to the X squared is going to equal KSP. Okay so far? Okay. So that's going to equal 2 squared is 4. X squared times X is X to the 3rd, right? Sorry. Get messed up, man. Because when we do, it was a 2 in front. So the 2's become the exponents, remember? The things we use to balance become our exponents. Right, in here. I just put it here to help us remember the word 2, so I took it out. I erased it out. There is. So when I squared 2x, I got 4x squared. Then I times it by an x, and I got 4x cubed. All I did was plug in right here into here and simplified it out. So I said, okay, every time I break up a strontium fluoride, I get 1 strontium. I get 2 fluorines. Now I put that back into my KSP. Mm-hmm. Okay, so now I'm going to look back up at my problem, and it said that the solubility constant for strontium fluoride was 7.9 times 10 to the minus 10. Now I've got to solve for x. So, because when I'm making a constant, anything that's a coefficient becomes an exponent. So I had this, this right here became this. Because you're actually doing it twice, right? Feels like you're doing it twice. So it's here, but it's also here, right? So it's like you're doing it twice, but you do have to do that. Right. Okay, so then I'm going to divide both sides by 4. So I'll get x to the 3rd. And what do I get on the other side? Sorry, I missed that. 975 times 10 to the negative 10th. Now I'm going to do a cube root. If you don't know how to do a cube root, you're basically taking this to the 1/3 power. I'm taking this to the 1/3 power. Okay? So when we get x, So all I have to do is take that number that I had and put it to the exponent of 1 divided by 3. What do we get? Good. And that is molarity, and that is the solubility of strontium fluoride. Okay? All right, so then we go to C. Okay, then we go to C. Let's look at C. You need more paper. Okay, I'm just going to read C while you're getting more paper out. C says an aqueous solution of strontium nitrate is added slowly to 1 liter of well-stirred solution containing 0.20 moles of fluorine ion and 0.1 mole of sulfate at 25 degrees. You may assume that the added strontium nitrate does not materially affect the total volume of the system, which really wouldn't be true because it really would increase the volume. So it wants to know which salt precipitates first. What is the concentration of the strontium ion in the solution when the first precipitate begins to form? So we had the KSP of strontium fluoride was equal to 7.9 times 10 to the minus 10. And they gave us strontium. I'm trying to find out, I've got 2 papers in my hand, I'm getting lost between the 2. Okay, strontium is said till it was 0.02 liter, 0.02 moles, and it was in 1 liter. So since it was 0.020 moles of fluorine in 1 liter, okay, and we didn't know what, that's just what they told us. An aqueous solution of strontium nitrate is added slowly to 1 liter of well-stirred solution containing 0.020 moles of fluorine. So this is going to be, because I got 1 liter on the bottom, that's going to be my concentration of F minus. Okay, so over here I don't know what strontium is. Strontium becomes my X, and this becomes 0.020 molar is equal to 7.9 times 10 to the minus 10. I'm solving for the strontium concentration. Yes, I do need to square it. Thank you. Okay. So solve for X here. Let's see what X is. And that's going to be my strontium concentration here. And I'm going to do the same thing for the KSP of strontium sulfate. But we didn't have anything squared on that one.
Wait, so we're just doing the algebra of my strontium?
Yep. So here, what's the strontium equal to? And then down here on this one, it told us that we had 1.1 moles in that same liter. So this is going to be equal to X times 0.10 mole per liter, 1 liter again. And we're solving for X down here too. 0.10, and it's divided by 1. We have a sulfate. So do we got the first one yet? I probably should call this a Y instead so we can keep a track of them. This one Y. 1.9 times 10 to the, that's off a little bit.
How much?
Well, I show that you should get 2.0 times 10 to the minus 6 molar. Okay, and solve this one for Y. So this one should be easier. We're just basically dividing it by 0.1, right? So this one would be 7.6 times 10 to the negative 7 molar. Okay, which one's a bigger number? It's hard to on the small numbers. Which one's a bigger number? Out of those two numbers, which is a bigger number? No, because you're dividing it by 0.1. Oh, yes, 6. Sorry, yes. It's negative 6. Thank you for keeping me in line there, Josh. Okay, so which one's a bigger number? Because they're really close. So is it 2.0 times 10 to the minus 6 is what compared to 7.6 times 10 to the minus 6? Well, ignore the 10 to the minus 6. 2 is smaller, so this one is bigger, right? So because that one is bigger, this one came from the sulfate. This was a strontium sulfate on this side, right? And this is the strontium fluoride on this side. Since this one is smaller, it will precipitate first. It means that I can't put as much precipitate first. Means it won't hold as much in solution before it falls out. Where did you get lost? So all I did with the second K is we were doing K for both of these. We had been given to us, we've been given this concentration and we've been given this concentration. We knew the Ks were equal to something. We were solving for strontium. So we're trying to find out strontium in both of these. Okay, that's what became our X here and what became our Y here. So when we solved for it, we got this as our Y for strontium sulfate, and we got this for our X for our strontium fluoride. Here's our strontium fluoride compared to our strontium sulfate. Since our strontium sulfate can dissolve more, it's going to stay in solution longer than our strontium fluoride. Our strontium fluoride will start coming out of solution sooner. Okay? Everything's soluble to some amount because it's got a KSP. Okay? So on D, on this one, as more strontium nitrate is added to the mixture, a second precipitate begins to form. At that stage, what percent of the anion of the first precipitate remains in solution? So we come up to D. And on this one, we know that when strontium concentration is equal to that 7.6 times 10 to the minus 6, then we can determine our KSP for the strontium fluoride like this, because at this point we now are precipitating out the strontium sulfate, right? So it wants to know when the second precipitate starts to precipitate out, how much of the fluorine is left. So I now know, I know this KSP, I know this, I'm now solving for F minus. Okay, so I plug in everything I know. Extend the page again, I've got a long page here. Okay, so I know that this is equal to 7.9 times 10 to the minus 10. I plug in everything else I know. So I know strontium is going to be 7.6 times 10 to the minus 6 times, now I'm going to call this x, so it's going to be x squared equals 7.9 times 10 to the minus 10. Divide both sides by 7.6 times 10 to the minus 6. You get x squared is equal to what? 1 point something times 10 to the minus 4. Okay, where did I lose you? So all I did is just use the same KSP. When the other one starts to precipitate out, then that means strontium has to be 7.6 times 10 to the minus 6. Okay, so I plug that in. That's the KSP for strontium fluoride. I replaced F with an X, so that's where I got the X squared. So I just brought that down. Now I'm trying to get X by itself. So do we have that number right there? I'm not trying to put the two equations together. I'm trying to solve for X. .6. I got 1.04. Is that what you got for that? Okay, and then square root both sides so we can get just down to X. And we should end up with 1.0 times 10 to the minus 2. That's a horrible writing there. Let me do that again. 1.0 times 10 to the minus 2, and that's molar. Okay, now they want the percent left in solution. So then I go back up and say, okay, how much did I have to start with? Well, I had 0.2 to start with, and now I've got left 0.01, right? I'm just trying to find the percent fluorine left in solution. This is what I had originally up in the problem. This is what I have now. I'm going to times that by 100, and I'm going to end up with 50%. That's what I have left. And always label what you have. Okay, we've done our hour. So I'm going to stop it right here, and I'll see you tomorrow.